Question 9. Which change leads to a higher concentration of SO3 in the equilibrium mixture? In other words, shift the position of equilibrium to the right hand side. A higher concentration of O2 will, by Le Chatelier's principle, it will try and oppose that change, lower the concentration of O2 and react some of it away to make more SO3. So A is your immediate answer. Let's just check. Higher temperature, by Le Chatelier's principle, will try and lower the temperature. Well, it's an exothermic reaction, so it won't shift it to the right hand side to make more heat. It'll shift it to the left hand side. B is wrong. Lower the pressure. Well, I've got 3 moles on the left and 2 moles on the right, so increasing the pressure would shift the equilibrium to the right hand side to try and lower the volume. So lowering the pressure would go to the left hand side. Use of a catalyst, well, that doesn't change the equilibrium position at all. All it does is speed up the forward and backward reactions equally. So your answer is A. The results of an investigation of reaction between P and Q are shown, and I've got a rate equation. So what I do is I take 0.2 and I divide it by 0.6 and I raise it to the power that P is with respect to, which is a 1. And then I multiply that by 0.5 divided by this value here that I don't know. I'll call that concentration Q, and I raise it to the power that Q is with respect to a 2, and then I divide 0.4 by 0.8. So 0.2 divided by 0.6 to the power 1, because P is with respect to 1. 0.5 divided by Q. Q is the thing that I'm trying to calculate, squared, because Q, order with respect to Q is a 2, divided by 0.5. 0.4 divided by 0.8. So I'm just dividing each of these. Now these are going to give fractions, so I'm going to flip everything over. Instead of 0.2 divided by 0.6, I'm going to have 0.6 divided by 0.2. I'm going to flip this over, the concentration of Q, which I'm trying to calculate, divided by 0.5, squared still, and instead of 0.4 divided by 0.8, 0.8 divided by 0.4, that gives me better numbers. This is 3 to the power 1 equals Q divided by 0.5 squared. 0.8 divided by 0.4 is 2. Divided both sides by 3, so Q, concentration of Q divided by 0.5 squared is 2/3. Square root everything. Square root of 2/3, 0.66667 is 0.82. That's the square root. Multiply both sides by 0.5. 0.82 multiplied by 0.5 is 0.41. So that's close to answer C. The equation between sulfur dioxide and oxygen is shown below. In an experiment, 2 moles of sulfur dioxide will react with 2 moles of oxygen. The total amount of the 3 gases at equilibrium is 3.4. So it tells me how much sulfur dioxide I put in at the beginning, how many moles of oxygen I put in the beginning. I've got no SO3 made, but at the end the total number of moles of gases at the end is 3.4. What is the mole fraction of sulfur dioxide in the equilibrium mixture? Well, what I'm going to do is I'm going to say that the number of moles of SO3 is X. So I'll say the number of moles of SO3 is X. Since 2 moles of SO2 make 2 moles of SO3, the same number of moles of SO3, the number of moles of SO3 that are made are the same as the number of moles of SO2 that are used up. So if I start with 2 moles of sulfur trioxide and I'm making X number of moles of SO3, I must have used up X number of moles of SO2 to make X number of moles of SO3. So my moles of SO2 is 2 take away X. Number of moles of oxygen is half the amount of SO3. So half an X, 0.5X gets used up from the initial amount of oxygen. So 2 take away 0.5X is the amount of O2 that's used up. Total number of moles is 3.4, and the total number of moles of each of these in terms of X is X, number of SO3, plus 2 take away X, number of moles of SO2, plus 2 take away 0.5X is the number of moles of O2, and that equals the total value of 3.40 moles of gas in total. It tells you that in the question. So I'm going to say X take away X is nothing, 2 add 2 is 4, 4 take away 0.5X equals this value 3.4. take minus 0.5x across the other side and take the 3.5 across the other side, so 0.5x now equals 4, take away 3.4, which is 0.6, divide both sides by 0.5, x is 1.2. So the mole fraction is the amount of x, or the amount of SO3, divided by the total number of moles of gases in the mixture. 1.2 divided by 3.4 is 0.335. So my answer is B. Nitrogen reacts with hydrogen in an exothermic reaction, so this is exothermic, which change increases the equilibrium yield of ammonia but has no effect on the value of the equilibrium constant. Well, first of all, the only condition that affects the equilibrium constant is temperature. So as long as I don't change the temperature, there's going to be no effect on the equilibrium constant. But if I change temperature, it's going to affect the equilibrium constant. Now, what a condition that's not going to affect the equilibrium constant, so decreasing the temperature will affect the equilibrium constant, so I'm going to rule that one out. Changing the equilibrium yield, well, a catalyst won't work, so I can rule that one out. A catalyst speeds up the forward and the backward reaction by an equal amount. It's not going to increase the yield of one product over another, one substance over another in the equilibrium mixture, so it's not A either. It's either B or D. Increase the partial pressure of nitrogen. If you increase the partial pressure of nitrogen by Le Chalet's principle, try and reduce the partial pressure of nitrogen by reacting some of it away and making more ammonia. So your answer is B. Let's just check. Decrease the total pressure. No, increase in the total pressure. I've got 4 moles of gas on the left, only 2 on the right. Increase in the pressure by Le Chalet's principle, it can lower the pressure by reducing the volume. So my answer is B.